Next we are going to prove a theorem, and this theorem states that if S is a compact, connected, oriented n surface in Rn plus 1, then the Gauss map maps S onto the unit sphere Sn. That is, the theorem states that let S be a compact, connected, oriented n surface in Rn plus 1, exhibited as a level set f inverse of C of a smooth function f from Rn plus 1 to R with del f of p not equal to 0 for all p belongs to S. Then the Gauss map maps S onto the unit sphere Sn. Here we need to prove that this Gauss map maps S onto the unit sphere Sn, and here a function f from a set x to y is onto if for each y belongs to y there exists a pre-image in x. So for that, let v belongs to Sn. We need to find a point p belongs to S such that n of p equal to v. If there exists such a point p, then we can say that this Gauss map is a onto function. Now let's start the proof. Let v belongs to Sn. Consider the function g from Rn plus 1 to R defined by g of p equal to p dot v. If v equal to a1, a2, etc. an plus 1, then g of x1, x2, etc. xn plus 1 equal to x1, x2, etc. xn plus 1 dot a1, a2, etc. an plus 1, and it is equal to a1 x1 plus a2 x2 plus etc. an plus 1 xn plus 1. That is, if v equal to a1, a2, etc. an plus 1, then g of x1, x2, etc. xn plus 1 is equal to a1 x1 plus a2 x2 plus etc. an plus 1 xn plus 1, where x1, x2, etc. xn plus 1 is belongs to Rn plus 1. We have a result that any continuous function defined on a compact set attains its maximum and minimum on that set. Here S is a compact set, and the restriction of G to the set S is a continuous function, and hence we can say that the restriction to S of the function G attains its maximum and minimum, say at P and Q respectively. Now consider del G of P, which is equal to P dou G by dou x1 of P, dou G by dou x2 of P, etc. dou G by dou xn plus 1 of P. Here dou G by dou x1 is equal to a1, and dou G by dou x2 equal to a2, and etc. dou G by dou xn plus 1 is equal to an plus 1. So it is equal to P a1, a2, etc. an plus 1, and here a1, a2, etc. an plus 1 is equal to b. So del G of P is equal to PV for P belongs to S. Here G is a smooth function, smooth real valued function defined on the domain of F, and G is attaining its maximum and minimum at points in S. Hence by here we can apply the Lagrange multiply theorem. By using this we can say that del G of P is equal to lambda del F of P for some scalar lambda in R, and n of P is equal to del F of P by norm del F of P, and which implies del f of p is equal to norm del f of p into n of p. So here lambda into del f of p is equal to lambda into norm del f of p into n of p. That is pv is equal to lambda into norm del f of p into n of p. Consider the norm of this equation, which is equal to here norm pv is equal to norm v, and norm of this equation will be equal to modulus of lambda into norm of del f of p into norm of n of p. Here v belongs to Sn, hence norm v equal to 1 and norm of n of p is equal to 1. So 1 is equal to modulus of lambda into norm del f of p, which implies lambda into norm del f of p is equal to plus or minus 1. Hence n of p is equal to plus or minus pv, which implies Gauss map n of p is equal to plus or minus v. Similarly, n of q is also equal to plus or minus v. By following the same steps, we can say that n of q is equal to plus or minus v. Now it is remaining to check that n of q is not equal to n of p. Then if n of q not equal to n of p, then we can say that for any v belongs to Sn, there exists a point p or q in Sn such that n of p or n of q is equal to v.